All right, this is going to be AP Calculus Lesson 5-7. We're talking about graphical definite integrals. If you take a look at the unit guide, we can see that we are still on standard M for the rest of the unit, 5-7. And notice the difference here. So analytic definite versus graphical definite. Analytic was just dealing with the equations. Graphical is dealing with the graphs. So coming back to our setup, make sure you have this down. Go ahead and pause me now. Okay, so how do I do this problem? So this is the problem I'm trying to work on. I need to find the integral from 0 to 3 of 2 dx. So whenever I have a function, don't think about the dx, but just this number, that is the function that I need to graph. So what is the graph of y equals 2? This is kind of asking, what is y equals 2? Can we picture what that looks like in our head? So if you're picturing a graph that looks like this, you would be correct. And make sure that that does go through 2. This is the constant function y equals 2. So now I'm asking, what is the area under the curve between 0 and 3 of this graph? And that is a little bit new for us, and I'm going to write this down kind of in advance. When I'm asking for the integral, remember when I say integral, that means definite integral by default. Another way of thinking about this in terms of graphical definite integrals is the integral is the area of the function and the x-axis. So let's say that this is the area, and I'm going to say between. So between, abbreviate here, between function and the x-axis. The weird thing here is that you can have a negative area if it's below the x-axis, so just be aware of that. So let's go ahead and look at our function again. So what is the area between our function and the x-axis? So in between here and here from 0 to 3. So the cutoff, and I can draw that right here, is right here between 0 and 3. Now I need to find the area of that rectangle. Well, you can see that the area is going to be a 2 by 3, so I can label the area, this is going to be 6. And indeed, the answer here is 6. But why is it 6? So let's go ahead and do the analytic version of evaluating this integral. So I'm going to go ahead and erase this y equals 2. Sorry if you wrote that, maybe it's out of the way. But let's evaluate that analytically. So this guy turns into what? Well, it's 2x to the power of 0, so it turns into 2x to the power of 1, and then divide by 1. So it's 2x, and then evaluation bar, put that on, from 0 to 3. And what does that turn into? So I'm plugging in 3 first, the end first, so this is 2 times 3, which is 6, and then plugging in 0 next, minus 0, so minus, and then plug it in and get 0, and that gives me 6. So analytically, we know it's 6, but graphically, we can also see why it's 6. It's the area between the function and the x-axis. All right. So another way of thinking about this 2 dx, and I want us to all annotate this also in our notes, that this thing is asking for the area of the one rectangle here. So this is the area of one rectangle. So what do I mean by rectangle? Obviously we see a rectangle here, but that's not exactly what I mean. So what's actually happening, and I apologize that we have to kind of skip over this in need of pursuing the speed that we have for AP Calculus, but we have a bunch of infinitely small rectangles here. Each of these is a rectangle. If I can make the width of these basically 0, almost 0, the limit as this distance approaches 0, that would be the correct drawing. But go ahead and just draw a few rectangles to let yourself know that this whole shape is composed of rectangles. What's the area of one of these rectangles? One of these rectangles over here. Well, this distance here, in calculus, we call this our d of x. The difference in x as we move to the next x. And that's where this dx comes from. This is saying I'm taking the height and I'm multiplying by the width. So each of these has a width of dx. But what is the height here? How tall is this? It's 1, 2. So it's 2 by d of x. That's where this guy comes in. 2d of x is describing what's happening with our rectangle. Now, as d of x gets infinitely small, and that's what this notation means, it's saying take the sum when I have infinitely small dx's, and I'll find the area. So this s really stands for sum. So the sum of this function from 0 to 3. How many, if I count up all the rectangles, what would their areas be if I added them all up? All right, so also make a note that if it's above the x-axis, so this is above x-axis, that means it's positive. All right, so let's go ahead and work on our second problem. So this is going to be the integral from 1 to 4 of -3 dt. It's with respect to t, not x anymore, just a change of variable. Nothing fancy here. So what does the graph of -3 look like? So this is, again, asking, I can write down here where we're not going to write this time. F of x is equal to -3. Where does that guy live? So if I come back down here, draw a line through -3, that is the graph of -3. And I'm finding the integral, so I'm finding the area between the function and the x-axis. So this area below the x-axis. Okay, well, let's cut it off between 1 and 4. So I'm really looking between, and I can make this a little bit neater by making it a line. And I can do a dashed line too. Between 1 and 4. That's, oh, a little bit crooked. That's my cutoff. It's still crooked, isn't it? There. I need to make them perfect. There we go. So I'm looking for this area down here. I still feel like it's not straight, whatever. So what is this area? And before you shout out, oh, geometrically it's height times base, let's go ahead and look at this analytically. So if I'm taking the derivative analytically just with the equation, this is going to turn into -3t evaluated between 1 and 4. All right, so this thing, when I substitute, let's make this line nice. When I substitute this in, I'm going to sub in 4 first. So -3 times 4 is a -12. And I'm going to subtract, so this was my first one. I'm going to subtract my second substitution. 1 subbing in for t gives us -3, so -3. And this is going to be -12 minus -3. Negatives kiss become positive, and that's going to be a -9. Let's see if that holds up with our graphical analysis. I should be boxing our final answers too. Okay, well, graphically, what's happening here? I have a distance of 1, 2, 3 by 1, 2, 3, so I do have an area of 9. The reason why it's negative, as you might expect, is because it's below the x-axis. So go ahead and make a note of that as well. So we'll say this guy is below the x-axis, so it's negative. All right, perfect. And always be thinking, this is asking for the infinite number of rectangles, adding them up with a height and a width of dx to find what the area is. All right, perfect. All right, let's move on to our next slide. Again, here's the setup. Go ahead and copy it down, pause me. All right, now that you've unpaused me, let's go ahead and analyze this thing. So let's do the analytic version first. By the way, integration of a linear function, a little bit different than a constant function. We're actually going to have some slopes here now. So analytically, let's see what this is going to be equal to. Wrong color, let's change it to blue. Analytically, this is going to be, I had 2x to the power of 1. This is now going to be 2x to the power of 1 plus 1, which is 2. Divide down, divide by 2, and this is going to be x squared. So this turns into x squared. Oh, sorry, I should have been writing our evaluation bars because I've evaluated it now. So I'm evaluating it here from 0 to 2. I'm just simplifying it a little bit. So when I evaluate it, 2 gets plugged in, it's just x squared. 2 squared is 4. And that's going to be subtracting. Plug in 0, 0 squared is 0. So my final answer here is 4. Let's make sure that we get that in our graphical analysis. All right, so now we need to graph 2x. And again, what equation am I really graphing? I'm graphing f of x is equal to 2x, which is hopefully most of us know how to remember to graph. 2x plus 0 is another way of thinking about it. So the y-intercept is here at 0, and it goes up 1 over 2, and I guess the scaling of my axis kind of gave it away. So let's go ahead and make that graph. Oh, I don't want it to be a dashed line, I want it to be a solid line. Solid. So it looks roughly like that, where I go up 1, oh, it was a little bit off. Let's make the points first. Up 1 over 2, up 1, sorry, right 1, up 2, right 1, up 2, and finally our line. Okay, I'm going to get the slope right, and then I'm going to move the line to make sure it goes through those points. Perfect. All right, now I need to find the integral. Integral, again, is what? It's going to be the area between our function and our x-axis for this interval from 0 to 2. So what is our interval? Let's go ahead and make that as well. Our interval is between 0, don't need to mark anything, and 2. So there it is. And I need to find the area of this triangle. And a little bit of review of geometry. Area of a triangle is 1/2 base times height. And if you don't like that, and I actually don't like that, go ahead and treat this as a special type of rectangle. I always think of triangles in terms of their rectangle, although I'm sure a lot of us are rolling our eyes. Mr. Sandell, we know how to make or find the area of a triangle. But think of this as a rectangle. This is a 2 by 4, so it's 8. Find the area of the rectangle and then just half that rectangle. So this was 8, make it 4. So this is now going to be an area of 4. And is it positive or negative? It is positive because it is above the x-axis. All right, so let's go ahead and do the graphical analysis on the right-hand side. So this graph, the integral from 1 to 3 of t. So what is that going to look like? I have a function. Well, let's do the analytic analysis first. So this is going to turn into, this was t to the power of 1, so now it's t to the power of 2. Divide down, divide by 2. I'm really multiplying by half, or divide by 2. And again, there's no plus c, so don't worry about that. And yeah, I'm evaluating this between 1 and 3. So now let's sub those in. Subbing in 3 squared is 9, so it's 9 over 2 for my first substitution, and I'm going to subtract my second substitution. Subbing in 1, it's going to be 1 squared, which is 1. 1 times a half is a half. So 9 halves minus 1/2, and similar bases or similar denominators, which means we can go ahead and subtract straight across. That's 8 over 2, or 4. Box our final answer. So hopefully we do get 4 in our graphical analysis. This one is going to be a little bit difficult to graph. Well, I mean, it's easy to graph, but we'll have to be careful. So this is going to be t. Right, let's do the same thing that we did in our last problem. This is going to be f of t, not x, is equal to t plus 0. So again, our y-intercept here is 0. I'm going right 1, up 1, a slope of 1, right 1, up 1, right 1, up 1, right 1, up 1. And let's go ahead and make our arrow, our line. Let's not make it a dash line, a solid line. Hey, more or less. Those points should be going through them correctly, but they're not. They should in your graph. And again, I'm looking for the integral, so I'm looking for the area between the function and the x-axis, or the t-axis, I guess in this case. The horizontal axis would probably be the more accurate term. And I'm going from 1 to 3, so let's go ahead and make our lines from 1 to 3. So there's 3 right here, and there's 1. Okay, so I'm not looking for this triangle area, I'm looking for this trapezoid area. And if you remember the formula for a trapezoid, you could use that. But again, I don't like trapezoids. I like basic shapes, basically rectangles, if I can somehow get that. And on the AP Calculus test, you really only need to do rectangles and know that a triangle is half of a rectangle. So I'm going to divide this into 2 pieces. I'm going to say that those are my 2 pieces. I have a rectangle and a triangle. Now it's super easy. Rectangle, let's do this one first. This is going to be 1, 2 by 1, so this has an area of 2. And I'm looking for the area of the triangle, and again, I don't like doing triangles, I do rectangles. So here is my, oh gosh, it moved at the very end. Here's my rectangle, or a square in this case, but it's still a rectangle. And this area of the square is 1, 2 by 1, 2, so it has an area of 4, half of that, and I get a value of 2. All right, so I guess I should really be highlighting what area we're looking for now. So this area here is the one that we found. Oh gosh, I let go of the highlighter so it re-highlights over itself. This was the area that we're looking for. So in our notes, if you have a highlighter, that's great, but usually what's going to happen is you're going to highlight this way. You're going to just do a bunch of lines, say this is the area that we're looking for, like this. That way you know what shape. It's not this shape, it's those two shapes. So that has a total area of 2 plus 2, 4. Yes, we got the right answer. Perfect. Okay, I have a question. How could we check our work? How could we make sure that this line right here between these 2 points that we have for our interval, what if I gave you that this was 1, 1 and this was 3, 3? How could I verify that this line right here is indeed this equation t? Do we remember how to go between 2 points to make the equation of one line? So if you don't, here's your hint. Equals slope times x minus x coordinate. And then you just plug in everything. So we have, I'm going to choose the point 1, 1. So 1, 1. And what's our slope? It's right 1, up 1. So it's also a 1. And just going from here, I have plugging in, or just moving things around, y equals, I'm adding the 1 to the other side. Distributing the 1 just makes it go away. So it's x minus 1 plus 1. Oh, it shouldn't be an x there, huh? It should have been a t. Change of variables. My bad. Let's change that to a t, so it's more correct. This is all in terms of t, not x. And so this was t minus 1 plus 1, which is just equal to t. Y equals t. So we can get back here. All right, now let's move on to the integration of a piecewise graph, the last slide. All right, so integration of a piecewise graph, and this is a problem where they will give you some weird graph and they'll say find the area, find the integral of that graph. This is the graph of f. Find the graph, or find the area between 0 and 5. So how do we do these? Well, hopefully you have this setup done and you paused me already. So again, this is just asking for the entire area of the one rectangle. And this rectangle is more of a weird trapezoid hybrid. Let's go ahead and mark the starting and end points. So here I go. So it starts between 0, so it starts right here. I guess I can still do it with the dash line. And it goes all the way to 5. So here's 5. Okay, let's go ahead and divide this to make it a little bit easier to see. So if I divide this, before I divide it, proper steps here is to shade in the area that we're talking about. We're talking about this area right here. I don't know why I draw a line and then it gets like super pixelated, but I think we can deal with it. This is the area that we're looking for. All of these rectangles. So now let's go ahead and divide it up into those nicer shapes. So here's my division, and that's hard to see. Let's switch to red, so I think that pops out more. Hopefully that does. There's two shapes. There's a rectangle here and a triangle over here. So again, this triangle might be a little bit harder to see because it's really a rectangle. So let's divide it again here, and now I have a triangle, a rectangle, and a rectangle. And I'm going to make this obviously into my other rectangle because I like rectangles more than triangles. Perfect. So what am I going to do now? I'm going to simply calculate all these things, and this is going to be the area of this rectangle is 1, 2 by 1, 2, so that's 2 times 2, 4, and half of that is going to be 2. So we'll write a 2 here. Hopefully we can see this. A 2. Whoa. All right, and then this is going to be a rectangle. It's going to be 2 by 1, so it has an area of 2. This is also going to be a rectangle, which is 1, 2, 3 by 1, 2, 3, and that's an area of 9. Add up all of these. 2 plus 2 is 4, plus 9 is 13. Is that a positive or a negative 13? It is a positive 13 because it's above the x-axis. So we'll say this is equal to, or turns into 13. Perfect. And box our final answer. Let's move on to this one. So I'm finding the integral between -2 and 3, so -2 and 3 of g, all of these. All right, so again, go ahead and set up your starting and ending. So it starts or ends here, it starts over here, and now we need to talk about what is our area that we're looking for. So let's go ahead and make our lines, do our little bit of shading. We're looking for this area here, and it's always between the function and the x-axis. So I'm going to come down here for this function, come up here for this function. Perfect. All right, so now I need to find the area of each of these triangles, and triangles are easy to do if you do the formula, or I can make them into rectangles. So here's how you make them into rectangles. I'm going to go back to using green here. So make a rectangle just straight up from the base, and there's one of my rectangles. Let's make another rectangle for this triangle. Rectangle, rectangle, rectangle. Slightly off, but that's okay. Just be straight, please. That works. Okay. So now I'm going to go ahead and figure out what the area of all of these is. All of these rectangles are. So this is a 2 by 2. 2 times 2 is 4. Half of that is going to be 2. This is going to be it goes down to 2. So 2 by 2, 4. This is going to be a 2 almost, but it's below the x-axis, so this is a -2. These two triangles actually cancel each other out, and there's an area of 0 between these two triangles. What about this triangle? This triangle is a 1 by 1. 1 times 1 is 1, and I'm doing half that because it's a triangle, so this area here, I'm running out of room, I don't think it would be visible, so this is going to be 0.5. Therefore, all of these added up, this turns into 0.5. All right, that's all the notes I have for us. Go ahead and write your summaries. Thanks.